Hey everyone, hope you're well, hope you're looking after each other. So what we're going to do today is we're going to do an experiment where we model the decay or the random nature of decay of unstable particles, unstable atoms. So we don't have any unstable atoms lying around, but what I do have with me is some skittles, and we're going to use skittles to model the random nature of decay. Now how we're going to do that? Well, what we've got here is, if I show you one skittle here, you'll see that one side of the skittle has an S printed on it. The other side does not have an S printed on it. Okay? So if I was to drop that skittle, it would have a 1 in 2 chance, or a 50% chance of it lying or facing S side up. Okay? Just like, so there is no way that I can predict for certain every time I throw that it will land S side up. It could, there's a 1 in 50, there's a 1 in 2 chance, but there's no way I can tell for certain. However, if I have a collection of skittles, if I have, like I've got here, 52 skittles, if I throw 52 skittles down all in one go, then because each of them has a probability of lying S side up, as the probability is 50%, then if there's 52 that are thrown down, there should be about 26 that throw S side up. Now what we're going to do is we're going to use that to simulate the nature of decay. So every time I throw something, there's a possibility that the skittle radioactively decays, okay? And the sample is decayed. So in this case, the S, every time it lands S side up, it means that a particle has decayed, and I will move that to the side. And we're going to record how many turns it takes me to decay all of the skittles. Okay, we're going to start off here. We've got turn 0, so right now before we throw anything, we've got 52 skittles. What I'm going to do is I'm going to put them into a glass, and then I'm going to throw them down, and any that lie S side up are going to have radioactively decayed, and I'm going to remove them, and I'm going to keep count of the ones that I've got left. So, hope you've not got your headphones on. Right, so in this case, I'm going to just take the ones that have got an S facing up, and I'm going to count the number that are left over. All of these ones here I'm taking away have an S facing up, so they have radioactively decayed. Talk amongst yourself, guys. I'll probably speed this up. So, S, S. I'm going to be saying S a lot, guys. I'm going to sound like a snake. So, here we go, guys. These are the ones that are left over that have not radioactively decayed, okay? I'm going to count them really quickly. 1, 2, 3, 4, 5. Got 10 there. 15. 20. 25, that's lovely. So I didn't stage that at all. So almost, after turn 1, I've got 25 left. So a little over half. Now obviously there wasn't precisely 26 left because it is still completely random. I can't guarantee for certain, but the more skittles that I do this with, if I did this with 1,000 skittles, then the closer I would get to the probable number. Okay, so I'm going to do it again on my second turn. I'm going to throw it down again, and this should be a little bit quicker. So I'm going to remove again any that have got an S facing up. They have decayed, and they are going away. Oops, I didn't really want to decay. There we go. So I had 25 left, so hopefully I should have around 12 or 13, but you never know for certain. And so here I've got 5, I've got 10, I've got 12. So again, almost half. So on my second turn, I went down to 12 skittles. Again, almost half. It's really hard to be precise with this, obviously, because it is still a random decay. Right, so we've got 12 left. Hopefully, we should have 6 decay. And let's have a look. 1, 2, 3, 4, 5, 6, 7, 8. More this time. Okay, so we're left to 4 at the moment. So on turn 3, we've only got 4 left. So in this case, we should have 2 decay randomly. And this is where it starts to get really messy. Oh my goodness me, all of them landed up. Okay, so in this case, all of them decayed. 4 were all the way down. Now what I'm going to do is I'm going to plot a graph in a second, and I'm going to show it you, and I'm going to plot a graph of number of Skittles versus throws. And what we find, or what we should find, is that we should have an decay curve that looks something like this. It's actually an exponential decay. Okay, right, so those have decayed. So I'm going to chow down and I'm going to plot that graph for you guys. I'll see you in a second. Okay, so what you can see here is I plotted the data into a spreadsheet, and what you can see is that we have an exponential decay of Skittles. So we started off with 52, and each time approximately half decayed. We never knew exactly when each individual Skittle would decay, but if we had a very large enough sample, we can predict how much will decay over time. Now this leads us into something called half-life. Particles or radioactive material, if we have a lump of it, we can see that half of that radioactive material will decay in a certain amount of time. And when we do that, that's called half-life. So the analogy we've got here is a really, really nice analogy for the random nature of radioactive decay, and how we can show that we can't see one individual atom decaying, just like we can't see one individual Skittle decaying. But when we have a large enough sample, we see that on the whole, half will decay. If we have a smaller sample, just like we did at the end here, it's harder to tell because the probability affects it. Okay, so, well, that's it basically. Take care, everyone, and I hope you have a lovely day. Speak to you soon. Bye.